Hi, today we're going to solve a system of equations, and when we think of systems of equations, a couple of the first methods that come to mind for solving them are substitution and elimination. We're going to use elimination today, but not in the usual way. Just as a refresher, imagine an equation like this. We want to solve x plus y equals 3 and 2x minus 3y equals 1. Generally, the first step is to decide on one of the variables to eliminate. So let's say x. And then we want to make sure that the coefficients of x match. Well, in this case, the coefficient in the top equation for x is 1, and in the bottom equation it's 2. So what we would normally do is multiply the top equation by 2. So then that would give us the following equations. 2x plus 2y equals 6. With this bottom equation left untouched. And then we can subtract, eliminate the terms with x, so 2x minus 2x, the x's vanish, leaving us with 2y minus negative 3y, which is 5y, and 6 minus 1 is 5. And so we obtain y equals 1. We can then take this, substitute it back into one of these original two equations, and determine x. So that's typically what we do. We multiply one or perhaps both of the equations by a suitable integer. But in today's problem, we're going to do something perhaps not so common. What we have is to solve the following system of equations. The first one is x plus the fraction 3x minus y all divided by x squared plus y squared equals 3. And the second equation is y minus the fraction x plus 3y divided by x squared plus y squared equals 0. Now, the move we're going to make here is definitely unconventional. What we're going to do is the following. Let's erase this to make some room. Let's call this first equation, equation number 1. And let's call this second equation here, number 2. We're going to take equation number 2 and multiply it by I, the imaginary unit I. And when we do that, we end up with IY minus I multiplied to what we have in the numerator equals 0. And then we're going to add this equation to equation number 1. So here's what we have. Equation number 1. And we're going to add this new equation number 2 after we've multiplied it by I. So upon adding, we obtain the following. X plus IY plus this fraction minus this fraction, but those fractions have the same denominator. So we have 3x minus y subtract I times x plus 3y all over x squared plus y squared, and then equals 3 plus 0 is 3. Okay, great. In the numerator here, we'll expand this bracket so that we get the following. All over x squared plus y squared equals 3. And then what we'll do is we will take these two terms, factor out the 3, and then take these two terms and factor out a minus 1. So continuing up here, we have x plus IY plus 3 times x minus IY. And then factoring out a minus 1 gives us the following. All over x squared plus y squared. But now we see a little bit of repetitiveness of the terms, or at least some sort of symmetry. Here we have x plus iy, here we have x minus iy. Wouldn't it be nice if we could turn this term into something similar? Well, if we factor out an I, we get the following. But what is 1 over I? If we go off to the side over here, 1 over I, if we multiply that by unity, or I over I, we obtain I over I squared, which is negative 1. And so that's negative I. So what we can write then here is the following. And now we have x minus iy here and here in this numerator of the fraction. And then we have the conjugate over here outside x plus iy. So why don't we do the following? Let's let z represent the number x plus iy. And if we do that, well, what's 1 over z? Check this out. 1 over z is 1 over x plus iy. But if we multiply it top and bottom by its conjugate, x minus iy, what do we get? X minus iy on top. And then since we're multiplying conjugates downstairs, we're going to multiply the first terms, x squared, and the second terms, iy times negative iy. Well, I times negative I is just 1, and then y times y is y squared. So we obtain x squared plus y squared. But we see x minus iy divided by x squared plus y squared here and here. So why don't we replace this with z, this divided by this by 1 over z, and this divided by this by 1 over z. So x plus iy is just z plus 3 times x minus iy divided by x squared plus y squared. That's this quantity, which is 1 over z, minus I times this right here, x minus iy divided by x squared plus y squared. That again is this quantity, 1 over z. And that all equals 3. But now, why don't we multiply through by z? That gives us z squared plus 3 minus I equals 3z. And now a quadratic is spawning. So let's write it in standard form. Z squared minus 3z plus the number 3 minus I equals 0. Well, we can use the quadratic formula here to solve this. So why don't we go up here and see what we get. So z equals negative b, so negative 3, plus or minus the square root of b squared, so negative 3 squared, 9, minus 4 times ac, 1 times 3 minus I. All divided by 2a, so 2 times 1. But up here in the radical, we could distribute the minus 4, so we get minus 12. And then here we get a 4i. all divided by 2. And then 9 minus 12 is negative 3. So we have z equals 3 plus or minus negative 3 plus 4i divided by 2. Now, we could stop here, but z equals x plus iy. And x and y, we want the solutions for those variables. We want the values for those variables. So it's not going to help us to keep our solution in this form for z. Can we find out what the square root of negative 3 plus 4i is? Well, here's a clever trick. We're going to write negative 3 as 1 minus 4. Once we do that, we'll take note of the following. By rewriting the radicand as 1 plus 4i minus 4, that's actually a perfect square trinomial. And it can be factored as 1 plus 2i all squared. And you can check that. If we square this binomial, 1 squared is 1. This times this is 2i, but double that is 4i. And then this quantity squared is 2i times 2i, which is negative 4. So, if we do that, we have the square root of this perfect square trinomial, which is 1 plus 2i all squared. And we divide this by 2. And so therefore, z is nothing more than 3 plus or minus, well, the root of 1 plus 2i squared leaves us with 1 plus 2i, all divided by 2. And so if we look at the two solutions that we obtained for z, we have the following. 3 plus 1 plus 2i is 4 plus 2i, all divided by 2. And then we have 3 minus 1 minus 2i, which gives us 2 minus 2i, all divided by 2. And both of these simplify nicely to 2 plus I and 1 minus I. But of course, recall that z is x plus iy. So in this case, here are our values for x, 2 and 1. And our values for y are the coefficients here, 1 and negative 1. So this tells us, therefore, that when x is 2, y is 1, and when x is 1, y is negative 1. And these are the solutions to our system of equations. You can try it out, sub in 2 and 1 to both of these equations for x and y respectively, and then try subbing in 1 and negative 1. The equations will be satisfied. So I hope you enjoyed that. Thanks for watching. Please subscribe to my channel, give this video a like, and consider supporting me on Patreon.